Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to optics and the chapters of lenses and formation of images. This exercise was a previous one in the Brevet exams in 2016, first session, first exercise. The title of this exercise is Image Given by a Converging Lens. The aim of this exercise is to verify by geometrical construction that a converging lens cannot act as a magnifier unless the object is placed between its optical center O and its object focus F. For this, we consider a converging lens L and a luminous object AB. So, part 1, the object AB is at 2 cm from L. Okay, number 1. Reproduce at the given scale the above document on the graph paper. Notice that here they didn't indicate the direction of propagation of light, but we take it as in the same direction of the positive x-axis, which is from left to right. And whenever we need to reproduce, we always start by drawing the optical axis at the center, having the same direction of propagation of light. Then we place the lens L perpendicular to the optical axis at the center, and we use the correct symbol of a converging lens. And we know that the intersection between the optical axis and the lens L is the optical center O. Okay, so now the object focus, the point F, is located 2 divisions in front of the lens. This is the point F. Okay, and the point A is located on the optical axis 1 divisions in front of the lens. This is the point A. Moreover, the point B is located 1 division above A. A hat is found on B. Now let's trace the object. Moreover, the scale is given by 2 centimeters along the x-axis and 1 centimeter along the y-axis. So this is it for part 1. Now in number 2, they are telling me specify on the reproduced figure the position of the image focus F' of the lens L. So we know the position of the object focus, and we can deduce the position of the image focus F' because we know that F and F' are symmetric with respect to O. So by specify, it means that we need to justify. So this is the justification. Now let's place the position of the image focus F'. So F' will be 2 divisions behind the lens. This is F'. Now in number 3, they are telling me show that the focal length of L is F is equal to 4 centimeters. So in other words, we need to calculate the focal length graphically, because now we know the position of the image focus and we already know the position of the optical center, which is the point O. So we always start by writing the definition of the focal length. The focal length is the distance from the optical center to the image focus. So the focal length is equal to the distance from the optical center, which is the point O, to the image focus, which is the point F', and we don't forget the bar because this distance may be positive or negative. So now the focal length F is equal to O F' bar, which is the distance from the optical center to the image focus, which is in the same direction of the positive x-axis. So the focal length is positive. And now we count the number of divisions between O and F'. We have 1, 2. And we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis. And this will give me 4. The unit of F is centimeters because the scale is in centimeters. So the focal length is equal to 4 centimeter. Always, all quantities in physics must have unit. And finally, it's a good habit to write our final answer in a box to make the task easier for the corrector to notice our correct answer. Notice that here the focal length is equal to 4 centimeters, which is a positive number, which verifies that the used lens L is a converging lens, because we know that for a converging lens, the focal length is positive. So now we have reached part 4. Let me make some space. They are telling me construct the image A1, B1 of AB given by L. So we need to construct the image A1, B1. In order to construct the image, we need to trace the path of two luminous rays, and the image will be intersection of these rays, okay? And here they are telling me construct, and we know that the word construct means that we need to trace and justify. So first, let's trace the path of these two rays. The first one that we'll consider is parallel to the optical axis, and we know that it will emerge passing through the image focus. And the second ray that we'll consider is passing through the optical center. It will emerge without deviation. And we don't forget arrows on light rays, incident rays, as well as emergent rays. I repeat, because the word construct means that we need to trace and justify. So now we have traced the two rays. Let's justify their path. Then the first one, which is parallel to the optical axis, let's say that an incident ray issued from B parallel to the optical axis emerges passing through the image focus. Now let's justify the path of the second ray, which is passing through the optical center. So an incident ray issued from B passing through the optical center emerges without deviation. Okay, so this is the tracing and the justification of these two rays. Now we need to trace and justify the image. In order to trace the image, we require for the emergent rays to intersect, but notice that these two emergent rays, they don't intersect behind the lens, therefore we need to prolongate them backward. And always the prolongation of the emergent rays is always dotted. This is the prolongation of the first emergent ray, and this is the prolongation of the second emergent ray. They intersect at this point. So what does this point represent? Always the intersection of the emergent rays or the prolongations is the image of the object. Notice that these two ray prolongations are coming from these emergent rays that are coming from these incident rays that are coming from B. Therefore, this point is the image of B, and it's denoted by B1. Moreover, a hat is found on B directed away from the optical axis, then we must place a hat on B1 directed away from the optical axis like this. This is the hat. Now here the image consists of 2 points, A1 and B1. We have already traced B1, now we need to trace A1. Now A is the foot perpendicular of B on the optical axis, therefore also A1 will represent the foot perpendicular of B1 on the optical axis. And now let's trace the image. The image is dotted because it's the intersection of the prolongations. Now let's justify the tracing. Let's say that then the image B1 of B is the intersection of the prolongations of the emergent rays And what does A1 represent? And A1 is the foot perpendicular of which point of B1 on the optical axis. So this is it for part A. Now let's move to part B. Now in part B they are telling me specify the nature of A1, B1. Notice that here the object AB and the image A1, B1 are on the same side of the lens, which is in front of the lens. And whenever the object and the image are on the same side, this means that the image is virtual. Then let's say that since the object AB are on the same side, then the image A1, B1 is virtual. One can answer this question in another way. Notice that here the object AB is pointing upward and the image A1, B1 is pointing upward, which means that the object and the image are in the same direction, which means that the image is erect with respect to the object. And whenever the image is erect with respect to the object, then the image is virtual. Then we can say also that since it is erect with respect to the object, then the image A1, B1 is virtual. Okay, no need to write both answers. Either of them is accepted. Okay, so now in part C they are telling me determine the size of the size A1, B1 of the image A1, B1. Okay, so we need to determine graphically the size of the image, which is A1, B1. Size of the image A1, B1 now A1, B1 consists of 1, 2 divisions, and we multiply by the scale along which you have counted the number of divisions, which is scale along the y-axis, and this will give me 2. Because the scale is in centimeter, then the value of A1, B1 will be in centimeters. Therefore, the size of the image A1, B1 is equal to 2 centimeters. So let me write here in part B that the nature is virtual and the size of the image is 2 centimeters. So this is it for part C. Now let's move to part 2 of this exercise. Now they are telling me that the object AB is at 6 cm from L. Trace on a new diagram the image A to B2 of AB given by L. So we need to trace on a new diagram for the new position of the object, the image A to B2 of AB given by L. Now part 2. Number 1. So as usual, let's take the direction of propagation of light from left to right, then place the optical axis having the same direction. Okay. This is x prime, this is x, And now let's place the lens L perpendicular to the optical axis at the center. And the intersection between the lens L and the optical axis is the optical center O. The scale is given by 2 centimeters along the x-axis and 1 centimeter along the y-axis. Now we didn't change the lens, therefore the position of the image focus and the object focus will not change as well. Therefore this is the object focus f and this is the image focus f prime. But we have changed the position of the object AB. So it is now at 6 cm from L. This 6 cm represents the distance object lens. So 6 centimeters, and we divide by the scale along which you are putting data, which is the scale along the x-axis. And this will give me 3 divisions, knowing that the point A is on the optical axis and always the object is in front of the lens. This side is set to be in front of the lens and this side is set to be behind the lens. So 1, 2, 3, this is the point A, and the size of the object as well didn't change. Therefore B is 1 division above A and A hat is found on B. This is the object AB. And now what we have done so far is constructing the optical system and placing the object AB in its new position. And now we need to trace the image A2 B2 of AB given by L. They told me trace, so no need to justify. In order to trace the image A2 B2 of AB, we need to consider 2 rays issued from B. Then the first one we'll consider is parallel to the optical axis. It will emerge passing through the image focus. The other one is passing through the optical center. It will emerge without deviation. And we don't forget arrows on light rays, incident rays, as well as emergent rays. And now we need to trace the image A2 B2. Always the intersection of the emergent rays is the image of the object. Notice that these emergent rays are coming from these incident rays that are coming from the point B. Therefore, this point of intersection of the emergent rays will be the image of the object, which is denoted by B2. Moreover, a hat is found on B directed away from the optical axis. Then we must place a hat on B2 directed away from the optical axis like this. Let's place the hat. Moreover, the point A here represents the foot perpendicular of B on the optical axis. Then A2, the image of A, will be the foot perpendicular of B2 on the optical axis. Now let's trace the image. This is it for part 1. Now in number 2 they are telling me A2 B2 is the size of A2 B2. Compare A2 B2 with A1 B1. In order to compare A2 B2 with A1 B1, first we need to calculate A2 B2. Then let's calculate the size of the new image. Size. Now A2 B2 consists of 2 divisions, and we multiply by the scale along which we have counted the number of divisions, which is scale along the y-axis, and this will give me 2. Because the scale is in centimeters, then the value of A2 B2 will be in centimeters. Then the size of the image A2 B2 is equal to 2 centimeters. And now we are ready to compare A1 B1 with A2 B2. Note that in part 4.c we have calculated A1 B1 and it's given by 2 centimeters, and A2 B2 is given by 2 centimeters as well. And whenever we need to compare numbers, we either say they are one is larger than the other, or equal, or less, and in this case they are equal to each other. So A1 B1 is equal to A2 B2. Now in part 3 they are telling me indicate the nature of the image A2 B2. So notice that here the object AB is in front of the lens and the image A2B2 is behind the lens. Therefore, the object and the image are on opposite sides, which means that the image is real. Let's say that since the object AB and the image A2B2 are on opposite sides, then the image A2B2 is real. One could answer this question in another way. Notice that the object AB is pointing upward, whereas the image A2B2 is pointing downward, which means that the image is in an opposite direction with respect to AB, which means it is inverted. And we know whenever the image is inverted with respect to the object, this means that the image is real. Let's say that since it is inverted with respect to the object, okay. And now we have reached the final part, which is part 3, the conclusion. So they are telling me in both cases the size of the obtained image is larger than that of the object, but L acts as a magnifier only when the object is between O and F. Justify. So in other words, they are asking me about the role of the lens, and we know that the role of the lens can be determined from the properties of the image. So if the image is virtual and larger in size, then the lens plays the role of a magnifier. Notice that when the object is between O and F, and this corresponds to the first position when the object is at 2 centimeters from L, we know that the image is virtual, and they told me that in both cases the size of the obtained image is larger. Therefore, for the first position, the image is virtual and larger in size. Then let's say that since the image A1B1 is virtual and larger in size, then L acts as a magnifier. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.